Okay. So Mathematica is going to be a big help to us on this one. So Mathematica has a Fibonacci function, a factor integer function, and it looks like I scrolled down a little bit, a prime function. So Mathematica tells us, you want to know what the third prime number is? It's 5. You want to know what the fifth Fibonacci number is? It's 5. You want to know how to factor the integer 10? It's 2 to the first power times 5 to the first power. Okay? So we just wanted to go through the list of prime numbers and factor them and see if we ever got extra factors.
Yeah.
Right?
So
I'll scroll up, and this is checking through the first 9 prime numbers, which we know 2, 3, 5, 7, 11, 13, 17, 19, and 23. So the 19th Fibonacci number is actually 37 times 113.
So that's one where we got 2, so.
Right, we can even check that. So we'll do prime 8 is 19. And that's what that told us. And Fibonacci number 19, 4181. So I can do 4181 divided by 37.
This should give us 113.
Yeah.
And it does.
Okay. But that doesn't get us all the way there, because we only found 1. So let's go up to the 20, first 20 primes, or the first 19 primes.
So that definitely gets us
It
there.
looks like we've
even run with 3.
3, 1 there.
Yeah.
3, 1 at 19.
Yeah, but even we have a 2, 1 at 11.
So that'll get us
That-
there already.
At 11 we already got more than we needed.
Yep.
At the 12th prime we actually got 3 more.
Then we got 2 more at the 13th.
Yeah.
So we'll prove it wrong pretty fast.
Yeah.
It goes up.
So there must be an infinite number of primes because of the Fibonacci numbers.
Yeah.
And I want to come back to a point that you were talking about. Let me zoom in just a little bit. So we had the primes 2, 3, 5, 7, 11, 13, 17, 19, 23.
Yeah.
Right away we were finding prime numbers that we didn't have. Actually starting at the 4th one, we found 13.
Yeah.
That
Yeah.
wasn't in our list. Then we found 89. That wasn't in our list. Then we found 233, which was not in our list. So all the way along the way we were finding primes that weren't in our list.
Yep.
And maybe there's a way also there to try to deal with that. And maybe that's a way you could modify this proof to use the Fibonacci numbers in a different way to prove there are an infinite number of primes. But all we wanted to do was count the primes. So it's 1, oh, actually not 1. That's the problem. 1, 2, 3, 4, 5, 6, 7, 8. Now we're even. 9, 10, 11, 12. Now we're ahead.
Yeah.
And then we get way ahead.
13, 14, 15. We get way ahead.
Yeah.
Pretty cool, right?
It's a neat
Yep.
proof.
It's a neat proof. It's a proof that if you accept the Fibonacci greatest common divisor idea, you can understand.
Yeah.
And it's a proof that teaches you have to be careful. You have to be careful that you label the Fibonacci numbers the right way. Mm-hmm. You have to be careful to make sure that you notice that this first one's not prime, because 1 is not prime.
Yep.
And then you have to be just careful that you either find 2 that have 2, which we did,
Yep.
or 1 that has 3.
Yep.
And then I'm sure there's one later that has 4.
Probably.
Cool.
Maybe if we go up to 30, maybe we'll find one that has 4.
Yep. 25.
That one does have 4.
But the 25th prime is 97. And Fibonacci number 97 is 193
Huge.
times 389 times a little over 3 million times
61 million.
361 million.
Wow.
Pretty cool.
Yeah.
Yep.
All right, good work this morning, guys.